Hello, students. So, any doubts so far? Any questions related to the lectures? Okay. Okay, I assume like you are going through all the lectures regularly, yeah, and you don't have any doubts. Yeah, so everything is all right. Okay. Okay, if there is no question, we will go through the tutorial. We'll solve the tutorial problem. The homework, which is due coming Saturday. Some of the questions, those questions are based on both chapter 5 and 6. Yeah. And we are going to have some tutorial from chapter 6 today. Chapter 5 we had last time. Okay. Okay, so let's start with problem number 615. Okay, 615 is similar to the question which has been asked basically. So this I will not solve, so but I will just draw. So this one is like this, K and 3M, and you have M here. Yeah, so K like this. Okay, and the question says that using the adjoint matrix, okay, determine the normal modes of the spring mass system. So normal modes. Okay. Okay. So the question has been asked in the homework, which is similar to this one only. Okay. So not exactly I will solve this one. This is up to you. But however, the next question 616 is similar. Okay. So this also says that. Okay. Now for this one, when you say like adjoint matrix, it says that adjoint matrix, the same thing in 616. So 616 also says the same thing. However, in 616, the system is like this. So you have two disks. So one disk is like this one. Okay, so this is K, this is J, and this is K again, and this is 2J. Yeah. Okay, now this question says, for the system shown here, write the equation of motion. Equation of motion, that is one thing. Second thing is determine the normal modes. Normal modes using adjoint matrix. Yeah. Okay, so if you see these 615 and 616, both are similar. Both of them are asking to solve to get the normal modes using the adjoint matrix. So So we will take this one. Okay, so if you can solve this one, you can solve that also, number one. Number two is the kind of system that is 615 is similar setup is given for the homework. So that's why I'm leaving it on you. So you have to solve this one. Okay, now 616, how to solve it. Okay, so this is equivalent to the mass spring system only. So when you have a system like this, so you have K here, J to J. Yeah, so this is what it is, J to Z. Okay, now this is a rotational system. Yeah, and K is for the shaft, the stiffness coming from the shaft. So shaft will provide the rotational stiffness. Yeah, and to solve this kind of problem, you you can assume, like, let's look it from the right. Yeah, and then you can take it will have two displacements, right? So one displacement will be from here to here. Yeah, so let's call it θ1, and there will be another one which will be from here to here. Let's call it θ2. Yeah. Okay. Now we have to write the equations, and then how to write the equations. So we can draw the Fibonacci diagram. So the first one we will have for the first one we can have like this. So if you have moved by θ1, okay, then what happens? So because of θ1, this rotational stiffness is there. So if you draw just the discs, so number one disc. So let's say this is number one. Yeah, so let's write it number one, and this is number two. Okay, so what do you see? So on this one, okay, so on this one you have a which has rotated. This one is rotated anti-clockwise. Theta is anti-clockwise, and θ2 is also anti-clockwise. So if you assume θ2 greater than θ1, then what do you see? There will be two kinds of forces which will be acting on this one, right? So those forces will be, so we can let's draw even better so that it's more clear. So let's say it's like this. Yeah. So yeah. So now this displacement of the shaft is anti-clockwise by theta, and hence this will apply a opposite force on this disc, right? So there will be opposite force, and what will be the force? This opposite, there will be opposite force. So there will be opposite force like this one. And what will be the force? Force will be K times θ1 will be the force like that. Okay, now next one. Now we are assuming θ2 is greater than θ1. So this has moved θ1, this is θ2, and hence since θ2 is bigger, then we will see there will be anti-clockwise. We are looking from this side only. So there will be anti-clockwise force acting on it, and that will be equal to, okay, that will be equal to K θ2 minus θ1. Yeah. Okay. So see here, we are looking from this side, θ2 here, θ1 here. θ2 is greater than θ1 because the net effect is this θ2 minus θ1 is anti-clockwise, and hence there is a force acting on it anti-clockwise, which is K θ2 minus θ1. If you see here, you have rotated is anti-clockwise, and it will resist basically this shaft will resist the movement, and the force which will apply on this will be on clockwise. Yeah, so net effect, what we see will be, equation you can write, final equation will be k theta 2 minus theta 1 minus k theta 1, right? Okay, so both are k basically here. So k theta 2 minus theta 1, this it anticlockwise, so is positive, then minus this minus k theta 1 has to be equal to the rotational system it is, and hence there will be a mass moment of inertia which is j, and then theta 1 double dot. So this is our first equation. Yeah, we get the first equation. Now similar we can do. So this one is for number 1. Similarly, we can do for the number 2. So how does the number 2 looks like? So number 2 will be like this. Okay, so we are looking from this side. For number 2, if we have moved by theta, this is by theta 2, that is theta 2. So, however, there will be theta 1 movement here also, and we are assuming theta 2 is greater than theta 1. That means net effect will be, there will be movement of this, movement of this, which will be anti-clockwise. So if this has moved anti-clockwise, there will be a force clockwise on that, and this clockwise force will be there, and value will be k theta 2 minus theta 1, right? Yeah, and there is no other force. Hence the equation in the rotational, so you have since this is clockwise, hence we write minus k theta 2 minus theta 1 is equal to, this has 2j, so this is number 2, and the value is 2j here, right? So this will be equal to 2j times theta 2 double dot. Yeah, this is equation number 2. So combining them, we get, so okay, first write nicely. So this equation we can write j theta 1 double dot plus this will go this side, so will be k theta 1 and k theta 1 again, so 2k theta 1 minus k theta 2. So we write like this. So first equation will be j theta 1 double dot plus 2k theta 1, okay, this is double dot, minus k theta 2 is equal to 0. This was from first equation. From the second equation is this one, or you get 2j theta 2 double dot plus rather minus k theta 1 plus k theta 2 is equal to 0. Right? So this equation rearranged, it will look like this. So we have two equations, we can combine them into a matrix form. Okay, so the matrix form will be like this. So matrix form. So this is a multi-degree of freedom system. So matrix form, you can combine it, it will look like j 0 0 to j theta 1 double dot theta 2 double dot plus you have 2k, big K here, so 2k minus k k theta 1 theta 2 is equal to 0 0. So this is the value. Yeah. So you can see that you have a diagonal matrix here because you have theta 1 here. So there is no theta 2 here, and there is no theta 1 here. So you get j 2j here, 0, 0 from these two, and then you have 2k minus k minus k, k. So same thing, equal to 0, there will be 2, 0 here, so like that. Yeah. Okay, so this is the equation, and then we have to do the analysis. Yeah, and here it says like you have to use the adjoint matrix method. Okay. Okay. Then how to do it? Here we are interested in finding the free vibration problem, right? So free vibration problem. Okay. Since these are just a spring and mass, so this is equivalent to mass, this is a spring, and hence we assume that value will be means the x or theta 1, theta 2 will be something like this, a1, a2, and then sine omega t you can have, or you can have ei omega t also you can write. So you can write both. So let's write this is sine omega t will be the answer, and hence you can theta 1 double dot theta 2 double dot will be equal to a1 a2, and here you get minus omega square sine omega t simply. Yeah, and putting these values, first part, okay, this equation we have got, this is the first part we have got already. Yeah, now we have to convert into the eigenvalue problem, and after that we can use the adjoint method and all. Okay, so this we have this is the equation, this is the equation, this is the answer, one answer. Second thing is we have to convert that into eigenvalue problem. So in order to do that, so we will put this value of theta 1 theta 2 and theta 1 theta 2 theta 1 double dot and to here, this equation. Okay. So here if you put what do we get? We get j 0 0 to j, and then we have a1 a2 minus omega square sine omega t. Yeah, so this is one part plus. Okay, maybe we write on the next page. So because we don't have a space, so let's go to next page. Okay, so we get j 0 0 to j, then we have a1 a2, then minus omega square sine omega t plus k 2k minus k k a1 a2 sine omega t is equal to 0 0. Or okay, now what we see is sine omega t is common to both, so we can get rid of this, and finally what we get, we can combine them together, this and this. So and we can assume omega square equal to lambda. Yeah, and if we do that, we get this equation, we get 2k minus lambda j minus k, then okay, k minus 2j minus 2j lambda. Yeah, Okay. So here we get 2k minus j lambda k minus 2j lambda minus 2j lambda. Okay. And then we have a1, a2, and this is equal to 0. Yeah. So this is the equation we got. Yeah. And we can solve it. So one of the method that we have followed in the lecture videos, here, this is, we know that solution, sorry. If this is the linear equation, and we know that a1, a2 is a non-trivial solution, it has a1 is not equal to 0, a2 is not equal to 0, then it is only possible when the determinant of this is equal to 0, right? And then we can find out the value of lambda. This is the one method you can use, right? So you can just, that is for a1 and a2 to be non-trivial. Okay, we have to do 2k minus j lambda minus k minus k minus 2j lambda equal to 0. Yeah, determinant has to be 0. And we can solve it, right? So, or we can say 2k minus j lambda and k minus 2j lambda minus k square equal to 0. Yeah, and accordingly we can solve it here, right? So we can change the sign, so meaning that we can make like this: j lambda minus 2k and 2j lambda minus k square equal to 0, and we can expand it, right? So we have this equation. We can solve, we can find out omega, that omega will be the natural frequency, because since it has two, the number of freedom here is 2, it will have 2 natural frequencies, and those 2 natural frequencies will be solved by solving this one, right? And lambda equal to omega square, so omega n will be equal to root lambda. There will be 2 lambdas. Yeah, so there are 2 natural frequencies. Okay, now what is adjoint method? Adjoint method is like this. Okay, so let's say there is a matrix A. Yeah, so let's say matrix A. Yeah, okay, or let's call B because we have used A1, A2. So matrix B. Then what happens when you say B minus B inverse? Yeah, is equal to, this is adjoint B divided by determinant of B. So this is the definition of B inverse, right? And how do you make adjoint B? Adjoint B is the cofactors, right? So you take the cofactors and then you transpose it, right? That's what you do, right? So this one is the same thing. Okay, so that really means that, again, this comes from the mathematics. You already have the mathematics already, and in the book also it's given, so you can also go through that. But this is the basic definition: B inverse equal to adjoint of B divided by determinant of B. And then if you pre-multiply it by B, then what happens? B inverse will be equal to I, identity matrix by definition, and then you get B adjoint B divided by B. Yes, or B adjoint B is equal to I times B matrix, the determinant of B. So we have this one. Yeah. Now, same thing we can use here. What happens? Now B equal to, we take B equal to, our equation is, our matrix we can take B equal to K, sorry, 2K. So 2K minus J lambda minus K and K minus 2 J lambda. You have like this. And we know that determinant has to be equal to 0. Yeah. So since as B adjoint B is equal to I times B, that really means if determinant of B is 0, you put 0 here. So what you get? You get 0 multiplied by a constant 0 is being multiplied to identity matrix. That means it will make everything 0. So basically that will be a 0 only. So that really means is what? In this case, it tells you that since here B is equal to 0, B adjoint B is equal to 0 matrix. So basically you get 0, 0, 0, 0, right? Because this is 2 by 2. Yeah. So this is what it tells you. Yeah. Okay. Now, if that is the thing, now if B is like this one, what is adjoint of B? So we can find out. So B is given, adjoint of B is given by cofactors. Yeah. So in this case, what we get? We get here, this guy you get here. Then you get this here, you get this, but negative of that because of this, the row and column. Yeah, so you get minus K multiplied by minus 1, so you get K here. Similarly, and so on. Okay, so so what here you will get this value. Here you will get a K, this multiplied minus 1. Here you will get again minus K multiplied minus 1, and here you will get this value. Yeah. So adjoint B will be equal to from looking from K minus 2 J lambda. So K minus 2 J lambda, then you get K, then K, and then get 2K minus J lambda. Yeah. Now B adjoint B is equal to 0, 0, 0, 0, right? This is how you are getting. So that means first we write B. So our B is 2K minus J lambda minus K and K minus 2J lambda multiplied by adjoint B is K minus 2J lambda K 2K minus J lambda. This has to be equal to 0, 0, 0, 0. Yeah. So this is another method of solving for lambda basically. And what we will see here, just see what we will do. If you multiply this multiplied by this, then you will get the first one. So you get this multiplied by this one, right? Then this multiplied by this one plus this multiplied by this one. And that has to be equal to 0. Yeah, so let's multiply, we can find out. Okay, so that means we get 2K minus J lambda, 2K minus J lambda multiplied by K minus 2J lambda, right, minus K square. Yeah, so this multiplied by this one, then this multiplied by this one. This is minus K here. So minus K and K. minus k square, hence you get minus k square here. Okay, now next one. Look at this. So we are going to multiply this with this row. So 2k minus j lambda. So 2k minus j lambda multiplied by k, and the minus 2k minus j lambda. So you will see here, this is k multiplied to this minus k multiplied to this. These and this both are same. So this will be 0. Automatically it will be 0. So you can see that all other value you can find is 0. You can see yourself that you will get this equal to 0. Yeah. Okay. And then that really means that has to be 0, 0, 0, 0. And that tells you that this has to be equal to 0. Okay. So that tells you that again, this is the minus j lambda minus here. So we can make it here, go here, this here. So we can write j lambda minus 2k multiplied by 2j lambda minus k square is equal to 0. And the same equation we get here. If you compare with the earlier equation that we wrote, so making determinant equal to 0, you will get the same. This equation and the equation we got now, both are exactly the same. This, but long way, So just assuming determinant equal to 0 will do. Adjoint method, when you are seeing, you are doing the same thing. You are finding out this one. So basically, both the same thing. Okay. Anyway, so you can solve this one. Solve to find lambda, and this will give you eigenvalues. So we can find out. So let's do it. So we have j lambda minus 2k, and then you have 2j lambda minus k. 2j lambda minus k square equal to 0. Yeah, so then we get 2j square lambda square, right? Then we get minus, okay, so we get minus, and then we have minus 2k, minus is here, so 2k multiplied by 2j, 4kj. So 4kj, and then similarly here to here we have here to here, so kj plus kj multiplied by lambda, then we have minus plus 2k square minus k square equal to 0. Okay, or 2j square lambda square minus 5 kj lambda plus k square equal to 0. Okay, and from here we can find out lambda. Lambda will be equal to minus b, so 5kj minus b plus minus b square, so 25k square j square minus 4ac, so minus 4, so 4 here, 4 times 2, so minus 8, then j square, k square, so k square, j square, right? Okay, so 2j square, k square times 4, 8, k square, j square, and divided by plus minus root minus 4 divided by 2a. So here we have 4, a is this multiplied by 2, so we get 4j square. So this is, there will be 2 lambdas then. Okay, so you will get 5 and then plus minus 25 minus 8, So 17, so you have root 17 here, divided by 5, divided by 4, and then you have a kj, yeah, divided by j square. So k over j equal to 5 plus minus root 17 over 4 k over j is lambda or omega square. So you get two natural frequency. This is how you find out the, so which is equal to natural frequency square. So two natural frequency Wn1 n2, okay, so is equal to, you get 5 plus minus root 17 over 4 over 4 k over j square root of that. These are the two natural frequencies you get. Okay. Okay, now when you say the mode shapes or it says normal modes. What is the normal modes? Normal modes means how it will vibrate basically. Yeah. So since there are two disks here, so let us say there are two disks here. So one there is a connection via a shaft. There is another shaft here. So the vibration could be of two types. In one disk will go anti-clockwise and the other disk can go clockwise. Yeah. So this is normal mode. So I mean, like vibration modes, when you say like with a natural frequency, it is going to vibrate. But how? Whether both the disks are going the same way, both going clockwise or both anti-clockwise at the same time, or is it that one going anti-clockwise, the other clockwise and go like this? There will be two kinds of, basically you will see, either it will be going like this, you know, the shaft is going like this one, or one clockwise, one anti-clockwise. Yeah. So that we can find out. And if one clockwise and other anti-clockwise, by how much? How much does one go this way? By what angle one goes anti-clockwise? And by what angle the other one goes clockwise, for example. So if we have to find that, and how you find out? You have to find the eigenvectors. Yeah. So if you find the eigenvectors will tell you what exactly that. So normal modes are nothing but the eigenvectors, the A1, A2 that we assumed. What is the value of A1 and A2? Of course, like a free vibration, like if you have a spring and mass system and it is undergoing a free vibration, then the amplitude could be anything depending on the initial condition. Yeah. So your initial condition, if you have given a particular velocity at t equal to 0, then automatically its amplitude is decided. Yeah. So it can have various amplitudes. Free vibration for the same system, given the same system, a spring mass system, and if it is undergoing vibration, then it can have any amplitude. And how will you know what is the amplitude? This will either you measure it, see what is the amplitude, or you have to see what is the velocity at t equal to 0, and like that. So similar thing is here. If there are two things are different now. Here natural frequency is not just one, two kinds of natural frequency. One natural frequency will be for both going the same way, both anti-clockwise and both clockwise. There will be one natural frequency associated with this one. Okay. Similarly, if your normal mode is A1 over A2 is negative, then when one goes positive, one goes negative, means both are in different direction. This is the second mode shape, and the frequency with which it is going, it's a natural frequency, right? So it's possible that there are two modes. One mode is frequency is less, go slow. The frequency will be very low, so go slow. And the other mode may be going very fast. Yeah. So, and in actual life, there will be a combination of the two. Actually, it's possible that both the vibrations are there. Now, once you find out the lambda, you can find out the normal modes. And how do you find out? For that, you have to come back the original equation. And the original equation was this: the 2k minus j lambda minus k minus 2j lambda, and then you had a1 a2 is equal to 0. So here a1 a2 is the amplitude. Here a1 a2 is, a1 denotes how much this goes, a2 denotes how much this goes at the same time. If this goes by 1, how much will this go? Either it will go, let us say, if it goes like this one, we are counting is positive, a2 is also positive, then you know both are going in the same direction. If this one is positive, when this is positive, this is negative, then you know that both are going in the opposite direction, right? So frequency, natural frequency that you got, that tells you how fast that we got this one. This is natural frequency. This is telling you there are two kinds of natural frequency, and they're associated with different modes. Yeah. So if this mode or this mode, and the eigenvectors tell you how much you move this one and how much will you move this one and which direction. So now you have to find out a1 and a2. And how will you find out? We can find out like this. So you put now lambda equal to lambda 1. Lambda equal to lambda 1 equal to omega n1, let's say. Yeah, we can have omega n1. Let's say this is equal to, omega n1 square. Let's say this is the smallest one. There will be two natural frequency. One will be a smaller, 5 minus root 17 will be the smaller one, and 5 plus root 17 will be the larger one. Yeah, so smallest is 5 minus root 17, largest is 5 plus root 17. So let's say the first mode we are referring to, which has lower frequency. So in that case, lambda 1 will be omega n1 square, which will be equal to 5 minus root 17 over 4 multiplied by k over j to the power, not power, because we are squaring it. Okay, so it will be like this. If we put this value here, lambda value, then after solving this one, we will find out a1 and a2. This will tell us the mode shapes for this frequency, associated with this frequency. Means this will tell us what is the value of a1 and a2. Okay, so let's put this value here. Then what happens? Let's say this should be a1 multiplied by this, a2 multiplied by this equal to 0. So what it tells you? This tells you 2k minus j lambda 1 multiplied by a1 minus k a2 is equal to 0. Now here you can see that both the equation, in fact, you will get the similar thing. You will see that you cannot get the unique value of a. Both are dependent. Even if you take the second equation, this multiplied by this one, you can try yourself, and the value you get for a1 and a2 will be the same. I mean, you will get both will be linearly dependent. And why do you say so? This is because if determinant of this is equal to 0, that really means both are dependent, right? That really means that really means you can multiply with something here, multiply with something here, and if you add them, you will get a 0. That really means. Okay, now we have to solve this one. Yeah, and we can find out from here only a1 divided by a2 will be what? Will be equal to k divided by 2k minus j lambda. Yeah, so you can j lambda 1. So you can find like this one, okay? Or from the second equation also you can find out, even from the second equation also a1 over a2 will be equal to, so this multiplied by this, Yeah. So A1 over A2 is equal to 2k minus 2j lambda over k. So k minus 2j lambda, k minus 2j lambda 1 by k. Why? This is because k times A1. So k times A1 minus plus this one is equal to 0. Same thing you get here. So k times this one minus plus A2 times this equal to 0. So we get this one. Yeah. So A1 over A2 we get where k value you will know, j value you will know, and lambda 1 is you have calculated already. You put the value, you will get that one. Okay. Now, depending on the value of lambda 1, you will get either positive or negative. So you can find out. So for this A1, A2 will tell you these are the normal modes basically. Yeah. So this you get first one. Similarly, you can get for the second one. Yeah. So this is A1 over A2 equal to this, and similarly, A1, A2, 4 associated with omega n1, right? And this A1 over A2 associated with omega n2 will be equal to k minus 2j lambda 2 here, right? Over k. So these are the your value that you the x1, x2, in this case theta 1, theta 2. So basically you can write theta 1, theta 2 will be equal to A1, A2, and then sine omega t, right? And this is the solution you get where A1 over A2, or you can write a constant c or some other constant, say alpha. Yeah. So actually this theta 1, theta 2 is the free vibration. This is given by like this one, where alpha is a number. Yeah. So where rather we can write also write like this is equal to beta times A1 divided by A2 1 and sine omega t. So this is a general this is a normal mode. Yeah. So this is the basic this will be the basic displacements basically. So for theta 1 and theta 2 will vary like this one. Either you can write A1, A2, but we know that A1, A2 we cannot find out exactly. Yeah. So but we know that both will be in a particular ratio. A1 over A2 is a certain number, so we can write beta multiplied by A1 over A2 and 1, and then if this is A1, then this is A2. If you divide by A2 to both of them, then you know that if theta 1 is A1 over A2, theta 2 will be 1, and this is the first mode. Yeah. And similarly, second mode, A1 and A2 will be, you get two types. One you will get for lambda 1, the other you will get for lambda 2. So there will be two theta 1 and theta 2 associated with the different frequency. Yeah. Any question, guys? Any question?
Sir, am I audible?
Yeah.
Sir, so there won't be any common theta 1 and theta 2 here means for combined motion?
There can be a combined motion. It's possible. Yeah. So in general you can say the theta 1, theta 2 can be like this one. So theta 1, theta 2 in general can be like this, is equal to like theta 1 not theta 1. So say, let's call it beta 1. Yeah. So beta 1, and then we will have sine, not sine, a1 over a2 and 1, and this is for omega n1, right? And here it will be sine omega n1 t. See here, we have n1 t. Okay, so here, here we should have written here I. See here, depending on which we are talking about, omega will become here. See here, this omega comes from the eigenvalues. So we will have, we can write like this one. So one component plus beta 2 a1 over a2 omega n2 means value of a1 over a2 for the second eigenvalue, and then 1, and then sine omega n2 t. Actual vibration will be like this, a combination. And these are the normal modes. This is the first mode, this is second mode, and actual you are a combination of two. In the real life, you will see there will be a combination of the two. However, it is possible to segregate. Like if you enforce only this one, it's possible that only this will sustain. Yeah.
Okay,
yeah.
sir.
Is it clear?
Sir, yes, sir, it is clear. And more means, sir, which mode is corresponding to which omega? That how do we identify, sir?
See, you have found out lambda 1 and lambda 2, right?
Yes, yes.
Yeah, and omega n is, if square root of lambda 1 is omega n1, square root of lambda 2 is omega n2. So it's up to you which one you label, which is the first one. You can have that first one is the lower one, second one is the higher one. You can label like that also. You got it? Okay.
Sir, I mean, like the means in one mode, like both will be going the same way, and in the other one the opposite way. So which omega corresponding to which one?
So that's why that's what I'm trying to explain. See here. So you get lambda, right? And lambda, finally you get, you know that lambda equal to omega n square, right? And lambda is equal to this value you get. Now you see here, one is 5 plus minus root 17 over 4. One is plus, one is minus. Clearly, one is a small number. If you take minus 5 minus root 17, let's say root 17 is root 16. So 5 minus 4 divided by 4. So one about 0.25, you see. The other will be 5 plus 4, 9 plus divided by 4, approximately. So 9 divided by 4, that means 2.25. So one is 0.25, the other is 2.25, right?
Yes, sir.
Got it? Now,
yes, sir.
So let us say we call omega lambda 1 is equal to 0.25, right? Lambda 1 equal to 0.25, let's call it. Yeah. Now what are you going to do? You put that lambda here, 0.25 here, 0.25, and then you solve. Then you will get, automatically you will get A1 and A2 for this one. And here A1 over A2, if it is positive for this lambda equal to 0.25, then you know that both are going the same direction, because A1 over A2 is positive, so both are going the same direction. If you get negative, that means for omega n equal to 0.25, one is going positive, one is going negative. So hence the opposite direction they are heading.
Okay,
Got it?
sir.
Got it?
Yes, sir. Yes, miss. Yes, sir. That ratio, sign of that ratio.
Yeah. So ratio decided by ratio is a function of lambda. Depending on which lambda you put, you will get corresponding A1, A2, and not necessarily that you will get a negative number. Not like that. It's possible that you get both positive, but one get a smaller one, the other get the larger one. Maybe one you get less than one, the other get greater than one. So that means one. That really means one moving like this one and the other moving more at the same time, you know? like this. So one is moving too much, the other is moving too little, right? It could be one mode. The other mode will be my right hand, for example, is moving less and left is moving right, but both are going the same direction. It's also possible. Means I said one will be go like this. In this case, it will happen for sure. In this case, you will see that this will be going one clockwise, the other anti-clockwise. Yeah, both going the same direction. That you will see. But here idea is find out the lambda, put the lambda and find out the eigenvectors, and eigen ratio of those A1 over A2 will tell you what it will do. And that ratio is a function of lambda. Depending on lambda, either it will be positive or negative, or more than one or less than one, or whatever value. But it will tell you the behavior basically. And finally, the combined behavior, you can sum it up. And this one is normal mode number one. This is mode number two, and you combine them together, beta 1 plus beta v. This will tell you the combined mode of vibration. Okay, you got it, Tushar?
Yes, sir. Yes, I got it.
Yeah. Okay. Any other question, guys? Okay. Here, remember that these two are, so this one is eigenvector 1, this is eigenvector 2, right? This one, if you put lambda 1 and then you get A1 over A2 and 1, this one and this is eigenvector 1, eigenvector 2. Yeah, and they have some property. They are also orthogonal. Yeah, orthogonal property. That really means what? Orthogonal means what? Orthogonal means dot product will be 0. Yeah. So dot product of this vector and this vector will be equal to 0. And that's why you can have linear combination. Right? So that means both are independent. That really means they are not dependent on each other. This can sustain by its own, this can sustain by its own, and also there can be a combination also. It's like I and J, right? So X has no dependence on Y and vice versa, and hence you can have X, motion in X can be independent of motion of Y. Something like this. Yeah. Any other question, guys?
Sir, one last question. Like we solved with two methods, like one determinant equals 0, and then in adjoint matrix.
Yeah.
Does it matter in few questions, like there is simplify solving with one method, or is it the same way?
It doesn't matter. Both are same actually. In both of them, determinant equal to 0 is the property we have used. Here it is just like in your question, it says that use the adjoint method. So that's why we used. That's it. Use the adjoint matrix method. So we used it. If it is not a specific, then you don't bother. You just make a determinant equal to 0, and that will be faster. Faster means you are actually both are same only. There is no difference. Yeah.
Fine.
Because both are same statement, but looking at differently. Yeah.
Okay.
Any other question, guys? Okay. If there is no question, okay. So see you next week. Yeah. Also, the lecture number 18 also actually, which is posted, has the tutorial problems of chapter 7. Yeah. So the next big tutorial, we can have any questions you have, so I can answer your doubt. For tutorial of chapter 7, you can see the lecture video 18, which I posted already. It's already there. Okay, guys, see you next week. Okay, bye.
Thank you, sir.
Yeah, okay.
Thank you.